Hey everyone, so let's solve this LeetCode hard problem, maximum number of robots within budget. So before moving on to the problem statement, I would like to say we are going to discuss an important concept today. How do we find the sliding window maximum in linear time? Means without using any multi-set or set or priority queue, how do we find the sliding window maximum? Okay, so I will be discussing that approach. And yeah, I solved it in 14 minutes. So share your timings below in the comment section. So moving on, we are given n robots and we are given two zero indexed integer arrays, charge times and running cost. So charge time basically denotes that ith robot cost these many units to charge. Okay, and cost means running cost definitely denotes the number of costs required for it to run. And we are also given an integer budget. Now suppose we choose k robots, so the cost of running these k robots will be simply the maximum, means the maximum charge time required for any single robot, means the largest charge cost among the k robots, as well as the addition of k into the total sum of all the robots, their running cost. We are taking the sum of running cost. Okay, now we need to return the maximum number of consecutive robots we can run such that the total cost does not exceed budget. That means if we are given the entire robots from 0 to n minus 1, we need to find the maximum consecutive segment that we can choose such that we can, means the cost required to run these robots is less than equals to budget. Okay, and hence we need to return the maximum possible length. Okay, the maximum possible contiguous segment. So let's see, suppose given inputs. So if we have the robots as suppose this 0, 1, 2, 3, 4, we have 5 robots. So if we consider a single robot only, suppose 3, so 3, 2. So its cost will be what? Its cost will be maximum value 3 plus number of robots 1 into sum of running costs, so 2. So it will be 5, which is less than budget. So hence we can simply run the 0th robot. Now let's consider 2 robots 0 and 1. So we have 3, 6 and the running costs are 2 and 1. So in this case the cost will be the maximum of 3 and 6, which is 6 plus 2 into the sum of running cost, which is 2 plus 1 3. So it is simply 6 plus 6 12. This is also less than budget, hence we can choose this contiguous segment as well. Now let's try for 0 1 2. So we'll have the charge time as 3 6 1 and the running cost as 2 1 3. Again the maximum of charge times is simply 6 plus k into the sum of cost is 6, so which is equals to 24, and still it is like less than equals to budget, hence we'll be able to choose this contiguous segment as well. Now you see like the budget has already reached 24. If we include one more, means cost which has a running cost of 4, it will be increasing by a factor of 4 because this charge time is less than 3. Okay, so it will exceed the budget. So hence if we try for all the possible subarrays, the maximum output, means the maximum contiguous segment that we will getting is of size 3, which is the output here. Okay, so hence we need to return the maximum contiguous segment of robots that we can choose such that their running, means total cost required is less than equals to budget. So in this case the output is 3. Let's see another input. So we see like the charge time here are 11, 12, 19 and the budget is only 19. So if we try to run a single robot only, if we try to run this robot, then the cost will be 11 plus 10, 21, which is greater than budget. Let's try to run this first robot, so cost will be 12 plus this 20, so it is also greater than budget. And if we try to run the second robot, the cost is 19 plus 7, 26, which is again greater than budget. Hence we will not be able to run a single robot only. So means running more than one robot is also not possible. So in this case what we'll do, we'll simply return 0 because it is not possible to run any robots. So the cost means will be like the maximum contiguous segment that we can choose is simply 0 here. So what do we want to find here? We want to find the maximum length of any subarray, right? We want to find the maximum length of any subarray such that cost is less than or equals to budget. And the definition of cost, I hope, is clear. It is simply what? It is the maximum of charge times plus k into the sum of their running costs. Okay, so we simply want to find the maximum length of any subarray which satisfies this condition. So what will be the most naive way of solving it? Naive way of first would be to simply iterate all subarrays. Okay, we'll be iterating through all possible subarrays, and what we'll do, we'll iterate through all possible subarrays and see like whether given subarray I, suppose this is a subarray I to j, whether the cost of this subarray is less than or equals to budget or not. Okay, and if the cost is less than or equals to budget, then we simply like maintain a global variable denoting the maximum length, and the current length will be simply j minus I plus 1. So if the cost of this subarray is less than or equals to budget, we'll update our maximum to account this length as well. Okay, and hence we'll be able to find the maximum subarray which satisfies this condition. So how we'll do it? You simply run a loop. I will be denoting all the start points of the subarray, so it will be moving from 0 to n minus 1, and j will move from what? Will move from I to n minus 1. Now we have this subarray I to j. So what do we want? We want charge time array. We have the charge time. Since charge time of I to j, we want to find the maximum, right? We want to find the maximum value out of this. And in running cost, we have the running cost array. In this, we want the sum of values, sum. So we'll find these two values. We'll iterate in the charge time arrays for suppose k, I to j. We'll iterate and find out this maximum value. Then we'll iterate from in running cost array and find out this sum, means sum of all values, and the cost will be simply what? Cost will be maxi plus the number of robots. So number of robots here will be simply j minus I plus 1 and into sum. So this will be the cost, and we'll see like whether this cost is less than or equals to budget. So then what we'll do, we'll simply maintain like a maximum robots that we can choose continuously, and initialize it with 0. So in the end, if our cost is less than or equals to budget, we'll simply update this maximum robots value with the maximum of already calculated max robots and the number of robots that we are choosing currently, which is simply j minus I plus 1. Okay, so we can simply do that, and we'll be able to do this in like this will be running a complexity of n square, and we'll be finding this maximum as well as sum in big of n. Okay, for this subarray. So the overall complexity here would be of the order of n cube. Okay, so this will be like the most naive way of solving it, and we see like n here can go up to 5 into 10 to the power 4. Okay, so means approximately of the order of 1e5. So this will be approximately 1e15, which will give us daily obviously. So can we like optimize it to suppose the first step would be to of the order of n square. Okay, so can we optimize it? So obviously we see like for each subarray I to j, we are recalculating this value from the scratch. So maybe we can, means this maxi and sum, maybe we can initialize it here only. This maxi as 0 and sum as 0. Means this ith subarray is starting, means the start point is I. Now what we'll do, we simply update this maxi with this jth value. Means initially we had I till j minus 1. Now this j is getting included. So this maxi will be storing the maximum value of charge time from I to j minus 1, as well as this sum variable we will be having the sum values from I to j minus 1. So we'll simply account this j here. So maxi will be updated with max of the maxi so far, and the new value that we are having is simply charge times of j. Okay, and simply we'll update our sum with what? Sum will be increased by running cost of j. So instead of like iterating through the entire array twice, we got rid of this, and we are able to calculate the sum as well as maxi in constant time. So hence, and everything means this cost calculation remains the same only. So we are able to move from this n cube approach to order of n square. Now since the constraints are 5 into 1e4, so this will still give like 25 into 1e8, which will still give TLE, but this is like a better approach to solve, means to calculate this maxi values as well as the sum values in a running fashion. So let's see this code to get more clarity, then we'll be like looking for further optimizations. So what we'll do, we'll initialize this max robots that we can get with 0. Now we'll iterate through all possible start points, initialize with the maxi with 0, because the robots can go up to, means values are ranging between 1 to 1e5. Okay, and the sum can go up to like long values, because 5 into 1e4 into 1e5 can go up to 5 into 1e9. So we have taken it long for that purpose. Now we iterate through all possible endpoints. We'll update the maxi value as well as increase our sum. Now the current cost, it will be simply maxi plus j minus I plus 1 means the length number of robots that we have currently taken. This is the k, and into sum. And now if this cost that we have calculated is less than or equals to budget, we'll simply update the maximum robots value with the maximum that has already been calculated and j minus I plus 1. And in the end, we'll simply return this maximum robots. So we see the overall complexity for this approach is this takes big of n and this takes big of n as well. So overall complexity is of the order of n square. And this will be giving us TLE. So obviously we need to optimize this approach, and based on the constraints that we have, maybe we want some algorithm of the order of n log n, or suppose of the order of n. Okay, means something, or maybe n root n is also allowed. Okay, so we need to think of some algorithms which runs in this means complexity and gives us a correct outcome. Okay, so let's try to make some observations based on the patterns that we have already identified based on the problem statement. So the first step is to, what is the problem? The problem is to find longest subarray. Okay, we want to find the longest subarray. So what approaches can come in our mind? Maybe we'll be using something of the form of prefix sums plus hash maps. Whenever we want to find this longest or count or something, maybe we'll use this prefix plus hash maps. Or what we can do, we can use 2 pointers plus a sliding window. Okay, maybe we can do that. Or what we can do that, we can maybe find out, create a DP array, DP of j, which denotes the maximum length of the subarray ending at j. Okay, so it will be, means each DP will be calculating, storing the length. Maybe these approaches maybe you can think of. So let's try to see which can be the most optimal approach to think in the direction of initially, so that based on the brute force, which approach we can extend upon. So we see in brute force what we are doing, we are simply we have this I and j. Now for this I, the maximum answer that we'll be getting, this j will be increasing to some factor. Okay, this j will be increasing to some factor, and after that for j plus 1, for all forward values, the cost will be increasing, means it will be greater than budget only. Okay, so for this I, if we are able to somehow find this maximum right that we have, if we are somehow able to find this maximum right in log n or constant complexity, our job is done. So let's try to see it in a reverse manner. For if we are considering, suppose this right point j, what do we want? We want the leftmost I point, such that this I to j has a cost less than or equals to budget. Means such that this I minus 1, as soon as we include this robot to be part of our segment, the entire cost becomes greater than budget. And obviously as we keep on increasing, means including more robots, the cost is tend to increase only because all the values that we have are positive here. Okay, so hence for each endpoint, what do we want? We want the leftmost segment that we can get, such that this segment, this window, has the cost less than or equals to budget. So what we see, for each j we want some I, and that I should be leftmost. So can we try to maintain 2 pointers, because here we need these 2 pointers, and slide this window in such a manner that for each j that we have, the left pointer is initially pointing to this leftmost point only. Now as soon as we move this j to j plus 1, what will happen? We know as soon as we, for this I to j, this I was the leftmost point for this j. That means if we had included this I minus 1 to be part of this segment from I minus 1 to j, the cost would have been greater than budget. Okay, here cost would be greater than budget. So that means for this I to j, for this, as soon as we include this j1, for j1 the leftmost point would be lying greater than or equals to I only. Okay, leftmost point will be greater than or equals to I only. We cannot include this I minus 1, because we know the cost from I minus 1 to j only is greater than budget. So if we include I minus 1 to till j plus 1, the cost will further increase. So this will increase further, and cost means it will be much more than budget. So obviously taking this I minus 1 as part of the leftmost point for j plus 1 is obviously not feasible here. Okay, So for this j plus 1, the leftmost point will either be lying here or further forward, right? So what we can do is, as soon as we encounter this new value, what we'll do, we'll increase, means move this I variable forward till like cost is greater than budget. Okay, so we'll keep discarding the ith robot from our current segment and keep moving I forward. So this cost will tend to decrease at every step. So we'll keep on doing this till this cost is greater than budget. Okay, so maybe in this manner we can like slide window from left for each new robot. Okay, now for each endpoint we'll be able to get the leftmost robot which satisfies the condition for the continuous segment from I to j, and we'll be able to like update our result with simply the maximum result plus comma the current length will be simply j minus I plus 1. Okay, so hence we can use like 2 pointers to solve this. Now comes the information about what informations do we need to maintain to find out this cost. Means till now we are simply seeing like whether applying sliding window is optimal here or no. So we saw like this I minus 1 will never be included in the optimal answer for this j plus 1. Hence, as soon as we move the window to the right, this left portion is keeps on decreasing. Means we can simply discard. Now for cost, what do we want? For cost, we want the max of charge times. We want the max of charge times, and plus it will be what? J minus I plus 1 into sum of running costs. Okay, this is like the cost function that we need to run. So there are two values that we need to come. Means j minus I plus 1 will be simply able to know because we are aware about the current j that we have and the current I that we have. So this value we will be able to calculate. We want this sum of running cost for the subarray I to j, as well as we want the maximum value in charge times array for the subarray I to j. So this sum we have already calculated so many times. We'll simply like we'll have this sum variable initially. Okay, initialize that with 0. Now what we'll do, we'll increase our sum with, when we encounter the right endpoint, we'll increase it with running cost of j. And when we like move this I forward, we'll remove its contribution. We'll remove its contribution from the sum value, so we will be decreasing it from the sum value. So as soon as we move this I forward, this sum will be getting decreased. Okay, so this means this sum value will be able to calculate. We have done it a lot of time. Now how about this maxi value? How will we finding this maxi? So what do we want? We have the range I to j, and we want the maximum in this range, and this range can change as well. Suppose initially the value this array was something of the form 4 3 1 2. Okay, suppose this was the range. Now currently I is here. Now this I can change, this I can move forward. So we need to like, maybe we need to find the maximum in this range in the next step. Maybe we need to find the maximum in this range in the next step. Okay, so as soon as we discard these elements, this maxi element we should be able to update. So which like data structure will be helping here? So obviously maybe we can think of, since we want the maximum element, maybe we can use priority queue. Okay, but we know like priority queue will definitely give the maximum element in this range. But what about the removal? What about suppose when we remove this value from, suppose the value that we need to remove is suppose not the maximum element. What if the current left that we have is simply 1 2 3 4, and this is the left part. Now when I moves forward, we need to remove this value from priority queue, but we will not be able to do that, right? Because obviously priority queue does not has access to like give iterator to a particular element. It only has the access to the top or the maximum element. Okay, so then using priority queue is not feasible. So what we can do here, we can either use a set, means ordered set, or a multi-set. So which is means feasible here? So we know like this charge times array that we need to find the maximum, it can have duplicates as well. Maybe the array was something of the form 4 4 3 3. Then what do we do in this case? We cannot simply store it in set and as soon as we move this I forward, we remove this. Then this set will only consist of the remaining values 3 only. So we need to account the multiple occurrences of each value. Hence, we will be using a multiset. Now when we use a multiset, what will happen? The element at the end means how will we suppose this is the multiset st that we have. So how will we finding the maximum element? So will be simply what? It will be the element present at the end. Okay, so you'll be able to get this maxi value using this iterator means the end value. And how will be updated? So as soon as we move this I forward, we'll simply remove the we will erase the occurrence of means charge times of I from this set. So we cannot simply erase means we can not simply call this function charge time of I. I hope you are aware, because if you do this, then it will remove all the occurrences of 4 here. Okay, so we need to first find the iterator pointing to this and then remove this single occurrence only. So how will remove it from a multiset? I hope this doubt is not there. So it will simply be, we'll first find this value from the set. Okay, so it will be charge times of I, and then once we have finded it, then we'll be erasing it, so that this only corresponds to a single element. Means if we simply find out st dot erase 4, if we call it, then it will remove all the occurrences of 4 from the multiset. So we do this in this form. Now at each step, how will we be able to get the maximum element? We'll be able to get this in this form. So what we'll do, we'll simply maintain two variables, left point to 0, j points to 0. Left is initially pointing 0. Now j will move from 0 to n minus 1. What we'll do at each step, we'll update our sum. We'll definitely update our sum and we'll insert the new value in our set. st dot insert nums of means we'll be inserting charge time of j in the set. So this will give us the maxi and this will maintain the sum in the range I to j. Now what we'll do, we'll move this I forward. We'll move this I till it is less than or equals to j. Means why we are moving it till it is less than or equals to j? Because we have seen the case here that there might be a condition that even a single robot we are not able to choose. Okay, so if we are not able to choose this single element as well, that means there will not exist this range 0 to 0 also. So hence we need to move this I forward, so that for the next j, when j becomes 1, we can account the range 1 to 1. Okay, and again if it not happens, then we can discard it. So hence we'll move this loop I, means we'll move I forward till it is less than or equals to j, and then what? And at the cost that we have currently, it is greater than budget. So while this is happening, we'll update our sum. How will update our sum? So we'll simply remove the running cost of I from a sum. So this sum will now have the sum from I plus 1 to j, and we'll erase the occurrence. So what we'll do, we'll simply erase st dot find what? Charge time of I. Okay, now we need to update this cost based on the new values that we have. So the maxi will be simply what? Maxi will be simply star of minus st dot n. So the cost will become maxi plus j minus I plus 1 into sum. Okay, so we'll be updating this maxi at each step and the cost will be able to get. And we also need to, one edge case here is also that as soon as this I, means I becomes less than equals to I becomes equals to j, this set will not be having any element. So hence this maxi that we'll be having, it will means will not be able to get this iterator, means this will give memory reference cell. So we need to check before we find out this maxi, we need to check whether the set has some elements. So means the size of set should be greater than or equals to 0, greater than 0. Then only there will be existing some maxi element, right? This is the case where I becomes equals to j and we have removed this I. That means we have expired the current segment I to I. Now we'll be moving this I forward. Okay, so for the next j, it will be I plus 1 to j plus 1. So we know like we'll not be able to get the maxi, so hence we need to do this check as well. So this covers all the cases, and now we'll simply increase our I. till this is happening. And then what we'll do now, when we have reached a, it will be sure that either like j is here and I is equals to, means I is pointing to j plus 1 if we are not encountered, or like I would be here and j would be here. So we'll be updating our max robots with j minus I plus 1 for this case. And in this case, if we simply use this formula, so it will be j minus I will be j plus 1 plus 1. So it will be 0. Okay, so we have handled this case as well using simple this formula. So we'll be updating our max robots count with this value. Okay, so we'll be maintaining the maximum in this case, and we'll be able to find out this maxi in log n time and this sum in constant time. And we'll be able to do this since this I and j will be moving at max to like n minus 1. So overall, they are both going to traverse through the entire array. So it will be taking a time complexity of 2n, and in the set we can have a maximum of n elements. So log n complexity will be there. So overall complexity would be 2n log n, which is like acceptable because n can go up to approximately 1e5 here. So let's see the code and implementation for this approach. I hope the entire discussion is clear to you now, and how we try to avoid other approaches and means went in the direction of 2 pointers plus a sliding window is clearer now. So let's see this implementation that we have. We means everything else remains the same. We initialize the max robots as 0. We have this left pointer, and now we'll be iterating through all the right pointers. We initialize this multi-set with 0, means with empty values, and we initially have the sum as 0. Now we insert the new charge time in the set and increase our sum. Now the current cost that we'll have, it will simply the maxi value plus k into sum. Now we'll use this loop till I is less than or equal to j, and this cost that we have is greater than budget. Now we need to remove the contribution of ith robot. So we'll remove that from sum as well as remove it from this set as well. And we'll update our, if set.size is still greater than 0, we'll update our cost with this value. And as now the cost has become 0 because there is no contiguous segments. We'll simply increase I, and then it is sure that cost is less than or equal to budget, or there exists no segment. So we'll simply update our max robots with j minus I plus 1, and this will be in the end we'll return max robots. So you see the overall complexity of this is of the order of n log n, which is acceptable here because the n can go up to 5 into 1e4 only. So I hope the algorithm as well as the implementation is clear. Let's try to submit this approach here. So this is the same means a code that we discussed. Let's try to submit it and see how much time it takes to run. It should run pretty fast, I think. It runs in 191 ms, which is fast, but it only beats 22% of the solution. Okay, so now comes the most important part of this problem. Maybe means currently we are having this complexity of what? We are having this complexity of n log n. So what if the interviewer asks us to avoid this log n and optimize it to big of n? Now, if you have not already not already heard about finding this sliding window maximum in constant time, you might wonder how we are going to solve it, because finding the maximum in a range, that means without using multiset, may appear how are we going to do it, because here without multiset, how will we maintain when we remove that, how will multiset will simply give us the maximum element. But without using multiset, is there any other data structure which runs in constant time without maintaining a sorted order? It doesn't, right? So how are we going to avoid this log n? And this log n is used to find this maxi value, right? So the problem now boils down to how to find maximum in sliding window. Sliding window in linear time. Okay, suppose for all the values in linear time, or constant for current window, big of 1 for current window. Okay, or big of n overall for the entire maximum that we need to calculate. Okay, so this is the main problem at hand that we need to solve to optimize the problem from n log n to order of n. Now let me show you, if we see the similar question section for this problem, we'll at the top we'll see this sliding window problem, sliding window maximum, which is a hard problem. Okay, so sliding window maximum is the same problem that we have solved here. We are not means this sum variable will not be there, but for each means window we need to find the maximum. So we can either use this multiset and do the same, but that was tagged as hard because means if this was a follow-up that we need to do it in overall complexity of order of n, then how will we do it? Okay, so this is the current problem at hand. So the algorithm that will be using it to solve this is, instead of a multiset, we'll be using a deque data structure. Okay, now how we'll be using and maintaining the values, let's discuss that. So suppose we have the example as charging times 36134. Okay, suppose we have the values as 36134. So instead of a multiset, we need to use a deque, and this deque will be using such a manner such that the front value of the deque, means the deque dot front, stores the maximum value. It stores the maximum value, and the remaining elements are stored in such a manner such that decreasing order. Okay, so suppose if 6 is the maximum value that we have currently, then all the other values that are present in like current window, it will be storing it in a decreasing order. Suppose the next value will be suppose 3, then 1, and so on. Okay, so suppose deque only has this value. Now how will we update it? So suppose this is the current deque and we have a new value as 4. So we want to know that for the current window we need this 4. Since 4 is the latest input, we need this 4 in the deque as well, and deque will be maintaining the numbers in decreasing order, and the front will obviously give us the maximum value in that input. So what do we want? This new value that we have, will keep pushing it from the back till it is greater. So since 4 is greater than or equals to 1, we'll simply remove this 4. Okay, since 4 is greater than or equals to 3, we'll simply remove this 3. So in the end, once we have removed it, since 4 is not greater than or equals to 6, we'll not be removing that. So in the end, the deque will have 6 and 4. Now why we are doing this? Because suppose we know like we'll need to move this I forward, right? So we need to check whether the maximum element that we present at here, whether this corresponds to this particular I or not. So if the index that corresponds to this maximum element is belonging to this I, then we can simply remove this value from the front. That's why means if we remove it, then why we are means maintaining element in decreasing order, so that as soon as we delete this element from the front, the second element is like the second maximum so far, and this will become the maximum. Okay, so as soon as we remove this, the deque becomes 4, and 4 will be the maximum in our current window. Okay, so we'll be able to like access the maximum element in the deque in constant time. Okay, so that's why since we are changing the window means from the left as well, so we want to maintain the elements in decreasing order, so that as soon as we remove the maximum element from the left, and if it corresponds to this ith index, then if we remove it, the second max element should now become the maximum. So we should have access to the elements in the decreasing order, because we want that we get the maximum from the deque dot front, means it should be a constant time operation. Okay, that is the goal, that was the goal here. Okay, so how will the deque change? For example, in this case, so if we have the I here, suppose deque initially was empty, now vi, so deque becomes 3. Okay, now if we have this 6, suppose currently this I is fixed, now I am currently just moving right. Okay, so how will this deque update? Now this 6 comes, so this 6 will remove elements from the back till it is greater than or equals to 3. Okay, so since 6 is greater than or equals to 3, it will remove this 3, and then the deque will be, this 6 will be pushed, so deque will become 6. Now we have 1. Is 1 greater than or equals to 6? No, so it will not remove it, but in the end it will get pushed, so the value will become 6 1. So that as soon as if we have the window currently as this, and now what do we want? We want to remove, means move I forward. So if we move forward, we will be able to remove this 6 and get the maximum as 1. So that's why we have removed, means maintain it in a decreasing order values. Now as soon as this 3 value comes, what we'll do? This 3 is greater than or equals to 1, so we'll remove 1 from the deque. Is it greater than 6? No. So we'll have 6 and 3. So now the values will be in decreasing order of 6, 3, and this will be the current window that we'll be dealing with. Okay, or the window can be this as well. Now what do you want? If we move this I forward, for this 3, since it is not present at the front, this will remain the same only. Now if this was the means the I, as soon as we move forward, this will be removed and the deque will be having 3, which will be maximum in this array. Okay, so in this manner the deque will be means the deque front will be storing elements in the maximum measure. So what the deque will be? Deque dot front gives the max value. New value comes. So we remove values from back till they are smaller. Okay, so what we'll do, we'll remove values from the back till they are small, and in the end what we'll do, in the end we'll push new value. Okay, and what happens when we shift the window? When we shift the window, shift window means we want to increase this I. In that case, what do we want? We want to remove this is if the front element was this I. So we know, like, instead of storing this maximum elements in this deque, we want to get whether the maximum element corresponds to this index or not. So instead of that, we should not store these maximum elements. We should be storing their indices 0, 1, 2, 3, 4. So instead of these maximum elements, we should be storing their indices. Here 1, here 3. Okay, here it was 0, then here it should have been 1, then it should have been 1, 2. Because we want to know, well, when we are moving this I forward, we will see like whether if this deque dot front that we have, if it is equals to this I, then we'll simply like remove this front. So since we have the operation of deque dot pop front, we'll be popping this element from the front. Okay, so that now this 2 will be the maximum. This element at index 2 will be the maximum. Index at element 3 will be the maximum. Okay, so that's why instead of the means pushing the element itself as part of deque, we'll be pushing them in the form of indices, and then we'll access it with what? We'll be accessing the max element as charge times of deque dot front. Okay, so this will give us the maximum in the current interval. So everything else remains the same, means the entire code that we used for this, everything else will remain the same. Instead of multiset, we'll be using a deque, and instead of finding the maximum like this, we'll be using it means charge times of deque dot front. And instead of simply inserting it, we'll be inserting it in such a manner so that it removes values from the back till the current value that we are pushing is greater than the back value. Okay, so let's see the implementation to means get a clearer means approach for that. So everything else remains the same. We simply used a deque. Now when we want to insert that, we'll be means check whether it is not empty or not, and the last value, that the new value that we are pushing, if it is greater than or equals to the value present at the back of deque, so we'll be removing that so that we maintain the decreasing order as well as we maintain the most recent information as well. So we'll be popping the values from the end, and in the end we'll be inserting the new value. Instead of the value, we are inserting the indices so that we'll see like how we'll be using it. So currently the cost will be simply charge times of deque dot front. Now when you want to move this I forward, we'll see like whether the front value or the maximum corresponding to the means the current window is the I or not. So that's why we use means we pushed indices instead of the element, so that this check is possible. Okay, because there can be duplicates as well. So this check means for means unique identification, this pushing of indices is necessary. So if deque dot front is equals to I, will simply pop it so that now this deque dot front will be updating with the second maximum that we had. Okay, and everything else remains the same. What we did, everything else is the same. If you see the code, everything else has been written in the same form. Just some minute changes has been done, and to find this maximum in like overall linear time, we have done this. So we see like every operation here is constant time, and this entire loop will be running an overall time of big of n, because means since values are either being pushed or being popped, so at max this pop operation will be happening for n times. Okay, so this will be like the big of n time approach for this problem, as well as the space that we have used is big of n. So I hope like you learned something new here. How do we find this sliding window maximum? Now you can try to solve this similar question as well, this similar hard question as well on your own, this sliding window maximum, and this will be a cakewalk for you. Okay, so let's try to submit this new code here. Initially we saw like it like beats only 22% of the solution. Now it should beat more because obviously we have moved from n log n to a better approach. Let's correct this and submit it now. So it should run like faster, means beats more than 22% of the solution, and it beats 73 and runs in 16 ms, which is pretty fast. So this is the most optimal approach for this problem, and this this, if this was the expected like approach or the expected optimized solution, then that's make this problem pretty hard. Okay, so I hope you learned something new and was able to grasp how this deque is storing the values in such a manner that we are able to access the maximum element in the sliding window in like overall linear time or means auxiliary constant time as here. Okay, so yeah, I hope you were able to follow along with all the approaches discussed here, and if you did, make sure to like as well as subscribe. And if you yet have any doubts remaining, make sure to means comment down. I will be happy to respond. Thank you so much for watching.